Hello, welcome to a new live stream. This is gonna be fun. The plan for today is that we're gonna start by continuing from where we left off the last time. So 2 weeks ago we started refactoring the bootloader, adding support for booting from hard drives. And hi everyone, welcome to my live stream. And today we are going to continue, and yeah, the first thing that the first issue we had was that the code is a bit messy, and I agree, the code is very messy, and I promised that I would fix it. Now I will not take a lot of time out of this live stream to do that. I will try to do it short. So I prepared a bit ahead of time so that this goes really fast. Okay, let me know if there are any issues, if you can't hear me well, if the music is too loud. Please let me know if there are any issues. Okay, so let's see where we are. Okay, this is what we had last time. So basically, in addition to the old run script, which basically worked from the floppy disk, we added this make disk image. So we added the disk image build steps, which create an actual disk, formatted disk, and then we had this debug disk, which this run disk, which runs Chemo using the hard drive instead of using this hard drive image instead of a floppy image. All right. So the first thing I want to change is I want to get rid of make. Now, let me just switch a bit to my face here. Make is a great build tool. Don't get me wrong about that. Make is a pretty good build tool, especially for operating systems. It is really flexible. You can do a lot of things with it, but there are some frustrations, some limitations. One of the things that I don't really like how Make handles is variables. Getting a variable is kind of hard to... Okay, let me just show you. I think it's easier if I show you. So, for example, here in this tool, in here. So, for example, yeah, a very good example is this make disk image script that we wrote the last time. So the script is called from over here. And the whole reason why we needed this script is because Make is terrible at, you know, being used for scripting stuff. It's very good at you know, resolving dependencies and handling dependencies, but when you have to script something, for example, the way we did things here in this make disk image script. For example, we are setting all kinds of variables. Doing this in Make is very difficult. Yeah, so I don't really like depending that much on shell scripts, to be honest. Some things are really hard to do in shell scripts, like, for example, we had some trouble with writing the LBA address. So basically writing raw binary to a file, which is really ugly. I think this is very ugly. You kind of can do it, but it's not the best. So the way I am going to fix this is by using Scons. I don't know how many of you have heard about Scons. Scons is basically a build tool which is built in Python, which is basically very flexible. One of the biggest advantages that I think is how easy it is to create, how easy it is to configure, how easy it is to, you know, set up variables and stuff like that. This is a big frustration for me with CMake, for example. And any of you who worked with CMake, you know that CMake has a lot of variables. Everything you do with the compiler, every compiler option will have an equivalent variable in CMake. And getting CMake to do something like building an operating system is a very tedious process. It is awful. I will not even go and touch any of the build systems which are built like in Java, like Gradle or any of those. And yeah, from experience, Scons has been one of my favorite ones. It is really easy to make it do what you want, and that's the basic idea. Alright, so I have prepared my scripts, and what I'm gonna do is just start copying stuff and explaining as I go. Alright, the first thing that Scons needs is, of course, to install it. So let's go ahead and do that. If you haven't installed it, the easiest way to install it is using pip, the package manager from Python. So let's see if I have the pip3 command. Yes, I do. So sudo pip3 install scons. And I already have it because I've already used it before. And now all I have to do is just run scons, and it will look for a construct file. And that's basically the first file you need to create when using scons. So let's go ahead and create the construct in the root of our project. Alright, now I don't want to waste too much time here, and I'm just gonna copy a couple of things from the stuff I already did. Okay, so these are basically some variables from Scons. I'm just importing them to make the compiler happy, because Scons will automatically import all of these things for us. Alright, and pathlib is basically a library which makes working with paths a lot easier. Alright, the first thing I am going to do is to create variables. And I'm gonna create this config.py file in just a moment. Variables is basically the way Scons deals with command line arguments, basically. But it's not only command line arguments. So, for example, if I want to do scons, I don't know, configuration equals debug. The way scons deal with this is by using these variables. They are a bit similar to how the arg parsing library work, the arg parsers from Python, if you're familiar with those. Alright, so what I'm gonna do here is I'm going to add a couple of variables. And the first variable is the build configuration, which this is the help string. Scons can also generate help, which is very handy if you are unfamiliar with the build system that a project is using. Scons will show you a help which shows you all the configuration options that you can set. Then the architecture, in our case we are using the i686, the image type and imagefs. These will be used to configure whether we want to create a disk image or a floppy image. We basically have, this is what we did here with these two files and with these targets from main. So, and then the image file system, this way we can select which file system to use when creating this image. Now, if we are creating a floppy image, FAT16, FAT32, X2 don't make any sense, so we will just force it to be FAT12. Alright, I also have a couple of more variables here. So these are enum variables. So Scons has a couple of variable classes, which are like the enum variables, and there are a couple of more. I don't recall them right now, but if you just want a plain string variable, you just use the add method. And I also want to add the image size, which will tell our build system, you know, we want to generate an image, we want to generate a disk which is this big, and then the toolchain, which will contain the path to the toolchain directory, which I'm using this one right now. Now the thing about the toolchain, because I'm creating a lot of branches and I'm cloning the repository a lot of times, and I think I committed that by mistake, is I'm using basically a link, and I'm linking to a folder where I had all the toolchains, so I don't have to build the toolchain every time I do a clone. Because these take a lot of space. These take like 2 gigs or something like that. Alright. Okay, next we have the environments. Alright, so the way this works is in Scons you have environments. So every build tool that you use basically uses all the variables that you declare in this environment. So let's see how this works. So here we had basically 2 sets of variables. We had these C flags, ASM flags, and so on, and then we had the target and target ASM flags, target C flags, etc. This is how we did this in Make. In Scons we can use environments for that, and these are very, very, very useful. And okay, let's start by defining the host environment. So we are creating this variable called host environment, which is an environment. This is imported here from Scons. We are using these variables that we declared over here. Scons will basically put all these options that we set here. It will just put them inside this environment. We are inheriting from the operating system's environment variables. So if we do, like, I don't know, for some strange reason we want to use, okay, so maybe not strange reason, but maybe we want to use CLang instead of GCC, we can just do this, and Scons will inherit this CC equals CLang variable, and then Scons, and then the rest of the command. All right. So what I'm setting here is that's another thing. So CC flags is basically used for both C and C++ compilers. C flags is only for C compilers, and CXX flags is for C++ compilers. All right. Now, if the build environment is debug, then we want to maybe remove all the optimizations. But if we are building on a release mode, we will want to have the optimizations. So that's the next thing. Okay. Next, we will force the image type to be... so if the image type is floppy, we'll force the file system to be FAT12, as already mentioned, because it doesn't make any sense to use FAT16 or FAT32 on a floppy disk, because it's very small and it's not enough space for that. Okay, and then we are going to replace a bunch of variables. And okay, so the way this works is whenever you create the environment, you can basically use as many variables as you like. These will basically replace anything that is inherited maybe from the environment, or maybe from another environment, from the default environment, or whatever. So these will override everything. So, you know, adding these is the same as calling the replace method. Now, what I have here is just a bunch of strings, which will be used to print. They will be used when printing what Scons is doing right now. So instead of getting like the command line, it's just gonna say assembling source, compiling source, The syntax is the command, so as the assembler, cc c compiler, and then com str, com string or something like that. All right. All right. So now we have defined the host environment. We will use this environment to build stuff from the tools folder, for example, to build unit tests that we will have, and we'll talk about these in just a moment. Okay, a little bit later, not just a moment. So now let's go ahead and define the target environment. The target environment is basically going to be the cross compiler that we are using. All right, so first thing I'm doing here is basically taking this arch that I'm putting here and adding that platform prefix which GCC uses, like i686-elf. All right, and then I figure out what folder the toolchain is in, and then the bin folder, and then the GCC libraries. I forgot to add this depths. Alright, so I haven't really done this the nicest way, but basically all the dependencies that we are going to use, like what version of bin utils, what version of GCC, are declared in this depths variable. This is just something that I declared myself. It doesn't have to do anything with Scons. Alright. Now, what we are going to do is just clone the... Okay, hold on a second. Yes, so to create the target environment, we're just gonna clone the host environment. And this is another really cool thing of Scons. In make, you have to type everything by hand, but here you can just use clone and make the modifications that you want, which is really, really cool. Alright, so what we're doing here is just adding this platform prefix to all the commands that we are gonna use. And then I have these variables set up for the toolchain prefix, the libgcc folder, and these which I haven't really used for the bin utils and GCC URLs. Okay. And now we are going to append. Now append is a bit different, so you know, same as before, these are just like calling clone and then calling replace. But Scons also has a really cool function which is called append. And what append is going to do, instead of replacing whatever AS flags we have set up here, it's just gonna add them to the existing list of flags that we have declared here. We don't have any assembly flags here, but we have these C flags, for example, for using C99. Here we are just adding a couple of extra arguments, a couple of extra flags. Same for the C++ flags, same for the link flags. Then we are adding the GCC library, and the library path is basically like that -i -l. So it's the search directories for the libraries. Okay. Another thing we have to take care of is to add the to the path environment. We did this in toolchain here when we did export path, is to add the folder where these tools are, to add them to the path variable. So this is exactly what I did here. All right, then we are basically done declaring all the stuff. All right, then this command will make it so Scons generates the help for all our variables that we created above here. And then another really cool thing about Scons is that we can use export and import. Where this is relevant is because we can basically call these s-conscripts. So an s construct is basically the main file where the main build stuff is. And the Scons script is basically like the sub-modules that we have in our project. And we will have one for stage 1, we will have one for stage 2, for the kernel, for the disk image. We will create those in just a moment. Now, what is this deal with the variant directory? Two things. By default, Scons will build all the stuff in the source directory, which is something I really don't like. And by using the variant directory and saying the variant directory should be just build, if I do just this, then Scons will place all the stuff that it is building, all the object files, all the executables, to put them in the build directory. By default, it doesn't do that. By default, it puts everything next to the source file, which is not really cool. Now, what you can also do with these variant directories is to create separate directories depending on the configuration, on the build configuration. Say, we want to have, like Visual Studio is doing, you have a separate folder for the release and the debug builds. We can do this, and this is exactly what I'm doing here. So if we are basically creating a subdirectory in the build folder, which contains the arch. So all our files that we are building will be placed in build/i686_ and then the build configuration, debug or release. This way we don't have to rebuild stuff from scratch. We don't have to do like clean everything and then start over when we want to build for another target platform, or we want to build for another debug or release build instead of whatever we had before. Now for stage 1, I am doing something special here. I'm also adding to this variant directory, I'm adding the image file system, because in stage 1 we have this header here. And if we are building stage 1 for FAT32, then this will have a different length. It will have some extra fields here. If we are building for FAT12, then we can just delete this, and it will have a shorter size. And if we are building for the ext2 file system, then we don't need this at all, because the ext2 file system, in the ext2 file system, it doesn't have anything in the boot sector. The boot sector contains only the boot code. That's it. So I'm also adding this to where I build stage 1, the destination file system. And then I'm calling the all the Scons script files for the child files. Now duplicate equals 0. If you don't set this, Scons will copy all the source files into the build directory, which is also another annoying behavior that Scons has by default. By setting duplicate to 0, that doesn't happen. Alright. Okay, now once we finish our build, okay, I haven't talked about what these export things do. Export allows you to basically take this variable that we have here, host environment, and import it into this Scons script file automatically, or in whatever. No, it's not going to import it automatically. You have to import it. So export will basically put it into Scons list of variables, and import will make Scons find that variable and import it into the current script file, basically. So we are exporting these two variables so that we can import them inside a Scons script, in stage 1 a Scons script, in stage 2 a Scons script, and so on. And once we have created the disk image, which is going to be inside this image as Scons script, we are going to import that image. And because we want to use it for a couple of phony targets. So instead of having like what we had right now with a separate script for build, for run, we can do scons run and scons debug and scons box and so on. We will create this in just a moment. Okay. Now another thing here is that we want, what if somebody types scons run, but the image is not built yet? By using these depends, we are telling scons that, hey, run depends on image. So if you want to use the run target, then you have to first build the image, which is gonna be another very useful thing, because now we don't have to type that much, like scons and then scons run, yeah, and so on. So it's just a single command, scons run. That's it. Yeah, something to keep in mind here is how to clean. To clean, you'd use scons -c. So -c is to clean everything. All right. Yes, we have finished this as construct. So now let's create these scripts that I have here. And then we will go into each of the stage 1, stage 2, into each of the modules. Okay. So the first script is going to be this configure.py that I created here. Now, as I mentioned, you can use variables here in the command line to config, for example, config equals debug, but you can also set them inside a separate configuration file, and you don't have to change, you don't have to pass them every time you're running the command. And this is exactly what I want to do here. So config.py. And I'm just adding all the variables here. In my case, I'm going to set the toolchain to the folder where I have set the toolchains. But, you know, in your case, this may be just, if you're just cloning the repo, it would be like this. All right. Next we have this phony targets. Don't see it here because I forgot to import it. Okay, let me just import these as well. So we were gonna have this phony targets file and then this utility files. Phony targets.py. Okay. Now, phony targets, this is basically like a custom builder. This is how you create custom builders in Scons. Okay, so no, this is not a custom builder. This is just a function which will basically take this environment and it will call always build this alias, and then basically what we are doing here is this is the target and this is the command. So the action, yes, the action. So basically Scons is just gonna call this file with these command line arguments. In fact, it's not even that complex. It's even simpler than that because I am joining all of these here. So basically Scons will call this action. Okay, I have to show you a bit more about the code, and then I think I can explain it better. All right, let's skip this for now and we'll come back to it. Okay, utility.py. So okay, here we have a couple of things. First is this parse size function. Parse size is so that I can specify the size and also have this suffix. So for example, if I want to have a 200 megabyte image, I just do 200M and that's it. Instead of typing 200 and then 1000, this just makes it easier to do that. And I'm just using regex to do that. Regex is always fun, so yeah, just find the numbers followed by optionally a K, M or J, and then we just parse that and multiply by 1024. And this is 1024 to the power of 2, 1024 to the power of 3. Alright, globe recursive. It took me a while to figure out how to do this. Basically the way Scons deals with files is that each file is basically inside this FS module. So there's dir, there's file, and there's entry, which is like the base class for both of these. And each file has a source node. The source node is basically where the source code is, and a destination node, which is basically where the build file is. Okay, so in order to do a recursive globe, what I'm doing here is I'm basically using OSWalk to go through all the files inside this directory, inside this source directory. I'm appending all of the directories to this list, and then I'm trying to figure out the relative path to the wherever. Okay, so CWD is basically the current directory, the folder that Scons thinks is the current directory. And I'm trying to pass the relative path, and the reason why I'm doing that is because if we pass the absolute path, Scons will just again put all the build files in next to the source files, which is not gonna be nice. Okay, so I'm basically getting the relative path of each directory. So I'm doing okay. So what I want to say here is that this globe only works for files in one directory. It doesn't work recursively, and we're trying to make it work recursively. So all we have to do in order to achieve that is to just go through every directory manually and then call globe for each of these directories. And this will basically return a list of files from that directory and put them into this list. And we're putting them in a list and then returning the list. Okay, I also have this find index and its file name. Find index basically returns the index of the first item that basically matches this predicate in a list, and this is just Python stuff. And then is file name simply matches the file name, checks if the file name is okay. You will understand what this does when I get to the code. Okay, I am looking at the chat. I do live in Cluj, yes, and what else people are saying here? Okay, people are just using the chat to talk to each other. That's not a problem. Alright. Now, let's go to stage 1 and get rid of the makefile from here and create this conscript file. Okay, these are just some imports to make the editors happy, and this is so that we can use the stuff that we created here under utility, that recursive glob. Okay, then we are importing the target environment that we have exported here. This target environment, we are now importing it here. This line is just to make the Visual Studio Code happy, because otherwise it's just gonna put an underline that it doesn't know what this variable is, because it's coming from Scons. No, I'm not MBR, I'm Romanian. I don't have a fetish. Or build systems. Nope. No. Nothing of that sort. Okay, and now let's see what we have here. Okay, so I'm just taking this target environment, cloning it, because I want to add a couple of things here. I want to add a definition so that we can pass to the NASM assembler what file system we are using. So what I'm doing here is I'm adding this flag. -d is like it's the same as yeah, so it's the same as doing a define in assembly. And I'm setting that to the image file system that we are getting from this target environment, and then we are adding these link flags, and yes, we are going to change stage 1 so that we are also using a linker script here, and we will also generate a map file, which is going to be very, very helpful. You will see in just a moment. All right, now how do we okay, let's not spoil everything at okay, so to get all the assembly files in the directory, we're just gonna use globe recursive. We have to pass the environment, and then the pattern, which is boot.asm in our case. And all the input files will now be in this variable. Next, we want to generate object files from these variables. The way we do that is by calling environment.object. Scons will see that it has the ASM file extension, and it will note that it has to call the assembler in order to do that. So that's exactly what this will do. And finally, we want to link everything together in a program. So we are gonna call environment.program. The destination is stage1.bin, and the source is these object files. Finally, we are going to export. So this will basically return a file that we can consider the target. This is basically the target. Now Scons will put something in here. I don't care what this is. But the thing is that now we can use it in other scripts. We can use it. All right. And then we are exporting stage 1 so that we can use it somewhere else. Okay, now about that linker script. What is that all about? Okay, so linker.ld. And this is the linker script that we are going to use. So again, start is going to be our entry point, and we have to change a few things in boot.asm for this to work. The output format is going to be binary, and we are going to map this to address 7C00. This is exactly what this org directive did here as well. Okay, and then we are declaring the sections. Now I have, in addition to all the sections that you typically have in a project like this, like what we had here in stage 2. Here we also had this entry section, but in addition to this, I added the file system jump and file system headers. So basically, what I'm doing here is I have a special place for the file system jump, and I'm kind of forcing it to be right at the beginning of the file. So this file system jump is basically these two instructions: jump, short start, and then NOP. This is because the first 3 bytes of this FAT12 header is this jump instruction. And then FS headers basically contains all the headers for the file systems. In our case, we'll put all of this into this FS headers section. Then we have the entry. So we 100% want the entry point to be right after the headers, because this is a short jump, and short jumps are short. It kind of limits how far we can jump. I think 128 bytes is the absolute limit, 128 bytes or something like that. So we don't want to, the entry point to be too far down, too far ahead into the file. So we are putting it right after the header, right here. And this is why I created the entry section. This is just a symbol. I'm declaring this symbol so I can look it up later to build the image. You will see in just a moment how cool that is. Then we have the normal text section. This is basically all the code. Data, which contains the the modifiable data, the modifiable variables. RO data is the read-only data. And then we have this BIOS footer, which is AA55. We have this right here at the bottom of the file. So here we have this padding section, and then we have this AA55 footer. We don't need to put this into the into the assembly code anymore. We can just use the linker script to force it there. This is exactly what I'm doing here. So I'm forcing this to be at address 7DFE because here we are relative to this address basically, even though this is, so in the actual file this will be placed at address 1FE basically. And then the BSS section will be outside of the file, and this is another cool thing that we can do here. So BSS contains zero initialized global variables basically, and we can basically reserve and manage the memory beyond the our bootloader, beyond those 512 bytes, by putting them after the 512 bytes that we have here. Okay, so now we have the linker script, and now we have to modify the boot.asm so that we are using all these sections. Let me just open this linker script here so we can see it better. And let's make this a bit more visible. Okay. I can... Alright, so we don't need this org7c00 instruction anymore. Then, for this jump, I mentioned that it will be in this section, so all we have to do is just section.fsjump, and now Nasm will place this into the right section. Next we have this FS headers, the file system headers. Alright, and we don't need this padding anymore. Then we have the start section, the entry section. So section.entry. And okay, so I placed everything here up till these error handlers. Then we have the text section. Text is basically where all the code is, all the functions. Okay, I'm gonna put everything in there. Then we have these constants. These are basically constant, so let's put them into the RO data, read-only data. And then we have these, which are in the writable data. So section data. Okay, sorry, that's not the correct syntax. Did I mess this up here as well? No. Good. Now these two are just so these doesn't matter. EQ is basically like doing a define, but it's kind of different. It's not using the preprocessor, it's basically using NASM, but it's basically like declaring a constant, but it doesn't allocate memory for it. Okay, we don't need this padding anymore. Okay, for the moment, let's keep this in the data section as well. We don't need this anymore because we have already declared it in the linker script. And finally, we have the BSS section. So and this is basically where I'm storing this buffer, and now we can actually allocate memory to it. For example, I don't know, 256 bytes or whatever. We can reserve bytes for this. And I think I'm using this buffer to read the floppy sectors, so in fact it should be 512, but whatever, it doesn't matter. The thing is that this will be beyond the end of the file. Okay, so that's basically it for stage 1. Let's see what else we have. Okay, so now we are going to stage 2. Okay, a couple of imports, doesn't really matter what these are. Same as before, we are importing this target environment from the main Scons construct file, yes. And then we are taking this target environment and customizing it to work with whatever variables we want to change. And we are not modifying the actual environment, we are just modifying a clone of this environment. Alright, so again, for stage 2, we want to add the linker script, and we also want to have this stage2.map file generated. Okay, I think this might actually be a duplicate. Let me check if I've already done this. Yep, I have this already here. Okay, so I am basically adding to the path, to the C path. This is basically the list of include directories, and I'm adding the current directory, so I can use this instead of this. Okay, this is for C and this is for C++. And then I'm doing the same thing for NASM, so I can also include stuff in NASM. Okay, then we have the list of source files. Same as before, we had glob recursive to basically collect all the files in the current directory. And we are going to collect all the C files, all the C++ files, and all the assembly files. And again, Scons is smart enough to know that in order to build these, all we have to do is just call objects. So it will figure out which tool it needs for each of these files. Okay, now this is another change that I decided to make, is to add support for C++. And the most important thing, Now, okay. To add C++ support, we don't really have to do much. The most important thing is to basically add to call the global constructors, and I'm gonna show you the article about that. Global constructors, host dev. This is also something that actually applies to C, but in C we don't really have that many global constructors. You can define global constructors in C by using an attribute. I'm not sure if they show this here. Yes. So in C you can have global constructors by using this global attribute. But you don't really see this used very much. You could use this to run something before main runs, basically. In C++, global constructors are kind of important. Whenever you have any static class, you basically want to call the global constructors before you enter the main function. And the way you can do that is basically we have to link a couple of files. And we have to also create a couple of files. So we basically have to link CRT0 in this exact order. That's kind of a very important thing here. CRT0. This is a file which exists inside the cross compilers directory. Same as where the... Okay, let me just show you. I think it's... Alright, so if we go here into lib, GCC, we also have these CRT begin and CRT end.o files. Okay. Okay, so hold on a second. What is the deal with this CRT0? Okay, so CRT0 doesn't matter. So there is CRTI and CRTN. These are files that we will have to declare. And then CRT begin and CRT end are the ones here from the GCC library, basically. These two files here. Okay, in order to do that, we basically have to add two assembly files, crti.asm and crtn.asm. Okay. So, for crti.asm, we basically have to declare this init symbol inside the init section, which basically is like a function. So, what GCC will do, what the linker will do, it will put all this initialization code, it will put it right here. So it will basically fill out the rest of the function for us. And then CRTN is basically the end of the functions. So again, in the init and in the fini section, init is the global constructor, fini is the global destructor, basically. We do the opposite. We pop EBP, so this is just like the normal code that you see to set up the stack frame when you enter a function. So it's just a complicated way for GCC to generate a function that we can call that will initialize everything. So we have crti.asm. This contains this stub here, which sets up the call frame, and then GCC will fill the rest of the file with basically this crtbegin.o. And then this fini section, it's the same. But we don't really care about this thingy because the kernel never actually I mean, we don't really need to call the global destructors for the kernel because the kernel is never destructed globally. It's not going to be destroyed. It's just going to run forever until the system reboots or something like that. So this one isn't as important. The init is the most important part. Okay, now that we have these two files, we have to call that init function from entry.asm. The way we do that is we declare that init symbol as extern so that the linker can find it. And then we just need to call it before calling the start function from C. So right here. That's it. And now we have called the global constructors. You can test if this works by doing exactly this. Just create a function that prints something to the screen, assuming that the printf functions are initialized, all that these functions need to do is initialized, and then see if it runs or not. Alright, and then yeah, so this is another thing. We can basically just call GCC with all the flags that we would normally call and tell it to print where the path to the CRT begin.o is by using this command. I haven't really done this in my code here, but that is something that you can do. Here I had this stuff. I'm just using this, where was it? This libgcc path that I've set up here. But yeah, that's an easier way to obtain the path to this file. And okay, now let's see how we can make Scons deal with these files. And this is what I'm gonna do here next. All right. So what I'm doing here is basically here is a list of objects that Scons has generated. So Scons has generated the object files based on these source files, and now we are going to basically look inside this list of objects, and we are going to remove crti.o, which corresponds to this crti.asm, and crtn.o, which corresponds to crtn.asm. And the way we do that is by using the pop method and then using this find index that I created in that utility. Okay, so I'm trying to find in the list of objects, I'm trying to find the index of whatever file has this file name. So I'm basically in this function, I'm ignoring the path, I'm ignoring everything. I'm just looking at the file name itself and matching it with crti.o. All right. And then we can okay, next we are going to rebuild this list of objects by putting crti, which was this stub that we had here. Then whatever the GCC library contains, this crtbegin.o. Then all the rest of the object files that we have here. Then we are putting crtend.o, and then our ending stub, which is in crtn. This is the exact order in which we have to build the stuff. And all that's left to do is just call a program from Scons, which will build this, all of these objects. It will link them in stage2.bin. All right. And of course, we are going to export stage 2 so we can reuse it later. All right. Has this been clear? My explanation has been clear so far. Let's see what people in the chat are saying. All right. Has this been clear so far? Is what I'm saying making sense? Or do you want me to go over something again? Please let me know. I am looking at the chat. Alright, if there are... I don't see any questions. Okay, so let's go ahead and finish this as Scons script for the kernel as well. And this one will be very, very similar to the one we have in stage 2. I'm not gonna copy it, but yeah, so we just have to use the same CRTI and CRTN files here in the kernel. Okay, now the way the kernel is being called in this operating system is I don't have an assembly stub at all. I'm just calling the main function directly from the bootloader, so we can still call this finish function by declaring it here as extern, and then calling it right when we begin. And this will have the effect of calling the global constructors. Okay. All right, and now I'm going to create the Scons script, which it looks very similar to the one we had in stage 2. Same as before, we are adding all of these stuff. We're using the linker script, just generating the kernel map, adding these to the include folders, and this looks almost identical to the one in stage 2. There's not much different about this one. All right, now for the most complicated part of this entire build system, which is how we generate the disk image. All right, so for that I created a new directory. No, not there. Image. And the way I wanted this to work is so that inside the image folder I have a root directory, and everything inside this root directory will be placed into the image, because I had all of these, test.txt file randomly here in the repository. No, we're gonna do this cleanly. We're not gonna have random files anymore where they don't belong. And inside the image folder we will have a Scons script, and this will be a bit more complicated than the rest. Okay. And of course we can put stuff here, demo file, I don't know, test.txt, hello world. This is a text file. And I don't know, a folder, and another file in this folder. Whatever, doesn't matter. Okay, so the Scons script. Okay, for this I'm going to be using a couple of libraries. The parted library I'm using to generate the image, so instead of calling the parted command, I will just use this library to create the disk image. I will show you in just a moment how that works. And sh is a genius library. It is amazing. It basically allows calling stuff from the command line very, very easily. So we can call, for example, makefs and a lot of the tools from Linux in a very easy and Pythonic manner. And yeah, I'm in love with this library. It's a very cool library. All right. Enough talking, and let's get to work. So here we are going to import stage 1, stage 2 and the kernel, because we need everything to build this script. Of course, we are using the target environment. And now for the main, okay, I'm gonna start from the top and then go to the bottom. From the top, what we have is basically the root directory from this directory. And we want to take every file from inside this directory and put it in this root content variable. And then we will take that and together with stage 1, stage 2 and the kernel. So we are building a list of the inputs that we're going to use for the command. And then we are going to generate an image. Now the command builder in Scons basically allows me to use a function, or it can also be like a shell command. For example, I don't know, do something.sh, but it can also be a Python function, which is what I'm doing right here. All right. And for the output, is going to be an img file. Here I also added support in case we also want to add disk images in the QCOW format, which is used by Camo. But for the moment, I'm just using img images, and the output will be image.img. All right. And by using this action instead of just, because I could do here just action equals the command like this, but by using action I can also specify this string, which will be displayed when this is being built, which is very nice. It will just look nicer. Okay. And of course, we want to export this image so we can use it from the main construct. Yes. Okay, so now let's see how we build the image. Okay. All right, so let's just set up the target, the image target. This is what we are doing here. How do we build the image? That's a good question. So, whenever we are using as the action a Python function, it will have these three arguments: the list of targets. So this is where Scons will put the list of all the target files that we have declared over here. Then the sources, all the source files, and this is exactly why I did this, so that stage 1 is the first source file, stage 2 is the second source file, and kernel is the third source file, and the rest are the rest of the files that we want to put on the image. Okay, and now we are okay, so this source is gonna have as data type one of those node types from Scons. So it's like Scons node fs, scons.node.fs.file or .dir or something like that. And here we are just converting that to a string to make it easier to use. Okay. So if we are building a floppy, we will call a function called build floppy. Otherwise, we will call an image, we will call a function called build disk. And the reason why I have these two separated is I try to do them in the same function at the same time, but it's kind of getting a bit more complicated, because here we have an image which doesn't have any partitions. So building this image is a lot simpler, it has a lot fewer steps. And here we have to create a partition table, we have to create the partition, we have to mount the partition, and then we have to basically create the file system and all the rest of the stuff. So just to keep things simple, I'm keeping these separate. And of course, if the image type is something we don't recognize, we can just throw an error here. Okay, so how do we build a floppy? And let me just copy all the code for that. And this is how we can build a floppy. So we do have access to the environment, so all the variables that are passed down from these vars, they are passed all the way down here, so we can have access to them here and determine what image size the user has selected, whoever wants to build our operating system. So, but for a floppy disk, we're not gonna create like 720K floppies. We're just doing the normal 1.44 megs. That's it. We don't want to support anything else. So yeah, 1.44 megabyte floppy disk has 2880 sectors. The size of stage 2, I'm using the stat function to determine the size. This is just using like the file system to return the stat function from the Linux API to return the file size. And then to determine how many sectors this size is, we add the sector size -1 so that we can round this up and then divide by the number of sectors. And of course I have to add this sector size variable. Alright, so the first step is to generate the image file. What the equivalent for this in bash is build scripts. Okay, where did I have that? Actually, I had it in, yes, build scripts, generate floppy image. So basically we are at this step right here. We are generating a file which has the exact size that we want our image to be. It's empty, it doesn't have anything on it. It's just an empty file, so it's just filled with zeros and has the exact size that we want. Alright, and this is exactly what generate image file does. So I'm gonna paste this function as well. And we are passing the path to the file and the number of the size. And we're using sectors here because we don't really care about, we're not going to use exact number of bytes anywhere in this code, so sectors is good enough. Okay, and in Python, basically to write a random file, we can use the bytes constructor, which will generate an array of this size filled with zeros. And we are writing that to the file and then just closing the file. And yeah, we are opening it in binary. Okay, next we want to format using FAT12. And for this, we have this beautiful function here, create file system. Now, I've also used this function for generating the disk image, where we care and that's why I have this offset, but I will explain what this offset is when I get there. Okay. Okay, so basically what we are doing is, if the file system is FAT12, FAT16 or FAT32, we are calling mkfs.fat. And the number of reserved sectors has to be 1 plus whatever the sector, the stage 2 number, whatever the size of stage 2 is. And if we are using FAT32, then FAT32 has 2 reserved sectors. If you call mkfs.fat with the number of reserved sectors set to 1, it's gonna complain. So that's why I added this here. Okay, and then we are calling mkfs.fat. Now, this is the beautiful part about this sh library that I was telling you about. So we want to pass. So this is a positional argument, which means it's just gonna be like the mkfs.fat, and then the target, which is like, I don't know, image.img. Then f equals file system. Okay, so this is basically the fat size. So it can be 12 16 or 32. So I'm just taking this variable here and just getting the 1 and 2, for example, or the 16. This is the disk label. So doing this syntax is the same as doing -f. And if it's a longer word like offset, then this will work automatically to -- offset equals. So this is really cool, something I really like about this sh library. Okay. This number of reserved sectors and then the offset. Now this offset is specified in sectors, and I found a little trick here. I found a way to basically create a file system without having to mount the loopback device, which is really cool. So now we kind of rely less on creating a you will see in just a moment. Okay, then if the file system is ext2, I'm calling mkfs ext2 with the right argument, so same as here. All right, and if it's not one of these, then we just bail out. Okay, next we have install stage 1. And this is, I'm really proud of this install stage 1 function, and I will show you why. All right, so what I'm doing here is basically I am searching inside the map file that we are generating. I'm searching for this entry start symbol. And if you remember when I did this make floppy image at the beginning, I basically wrote the first 3 bytes, and then I had to pad the file so that exactly at 90 would be the words, so that the entry section is exactly at address 90 for all the file systems. But this is very wasteful because our space in stage 1 is so limited and we are adding padding bytes. We're just adding zeros that serve no purpose. And yeah, that was not cool. And this is the way I am addressing this. Instead of having to hard code this to like 90 or some value and just have to fill everything with zeros, what I can do is search inside this map file for this entry start symbol. And just take the address from there. And yeah, this is the find symbol in map file function. I'm just using regex to parse that file. I don't have one right... Actually, I might have one. Hold on a second. Okay, here it is. Kernel.map. So you can see, for example, if we want to find entry start, all we have to do is search for the line which contains our symbol and take this number here and parse it. And this is exactly what I'm doing here. I'm just searching for that symbol and parsing it in base 16. And then I'm subtracting 7000, so it's an offset in the file, not an offset in memory. Okay, once I do that, same as I did in this generate make floppy image, I'm writing the jump instruction in the first 3 bytes, and then I'm writing the rest of the bootloader starting from that offset, basically. So the main idea here is so that we don't overwrite the file system that the MKFS tool. We're not overwriting the file system headers that the MKFS tool generated for us. This is just more convenient. Then, yeah, so all the stuff that we have in all of these variables don't matter because these are not used at all. These are not used. we could just replace everything with, I don't know, instead of dB to use resb and then a number of bytes, like 8. And the code would work the same. Okay. Alright, so I'm writing the first 3 bytes, and then I'm writing the rest of the stage 1 bootloader to the file. Now, I will explain when I get to the disk what this offset is. Okay, the next step is to install stage 2. Oh yeah, and something I haven't done here is that we will have to do for this bootloader to work is to add this these bytes here. I haven't done this yet. Okay, we will get back to this after I finish with the rest. Okay, now install stage 2. This is actually a bit simpler than stage 1. All we have to do to install stage 2 is just write the stage 2 starting from this offset. Now I also had this limit to add a check, but I just didn't add the check at all. To make sure that we're not overwriting, for example, the first partition. If you remember from the last video, when we did the... Okay, so there are 2 cases here. We have like a floppy disk, and we have a partitioned image. So it's a okay, so let's just call this disk. Okay, you cannot see this. Okay, let me make this up. Okay, can you see this, right? You can see the board. Now, in a floppy image, all we have is the boot sector, which contains stage 1. And this also contains the FAT12 headers that we have talked about. So, and then we have the reserved sectors, and this is where we are placing stage 2. So this is a reserved area. And this is where we are placing stage 2. Okay, and then, yeah, so this is one sector. This will be however many sectors stage 2 is. And then we have the rest of the file system, the file allocation tables, the root directory, and so on. The rest doesn't matter. Now, if we have a disk, then things are a bit different here. Because in a disk, we start, of course, the disk will also have like a boot sector, but this is called the master boot record. So this is where MBR is. So this is just a piece of code which will basically search for the first partition, and it will load the first active partition. There's a little partition table right here at the end of this. So there's the partition table. Right here at the end of the MBR. So right here we have this thing, which is the partition table at the end of the MBR. Then we have some padding, some blank space. And this is where we are putting stage 2 in this case. So this space basically is just padding, because the partitions are usually aligned to cylinders. This is what the default behavior of Parted is, for example. But we can also force it to use a higher number so that we have more space. And then here somewhere we have the first partition. So we have partition. Okay, partition 1. And inside this partition 1, the first sector is where stage 1 is. Okay, is this clear so far? So this is the difference between how to create the floppy image and then the disk image. Okay, so the reason why I have this offset in the code when installing stage 1 and stage 2 is because I know where this partition begins, because I have called the parted command with the, okay, I gave it an argument telling it where I want the partition to start, what sector I want the partition to start on. So I know where this is. So all I have to do in order to install stage 1 properly is just pass the offset, which would be the sector number where the first partition starts. And that's how I can, I know where to install the first partition. Then for stage 2, we don't need, for stage 2, it's always gonna be starting from the second sector. On a floppy disk, it's gonna be in this reserved section of the file system, and on a formatted disk with partitions, it will be in this blank space between the master boot record and the first partition. Okay, so this is what I'm doing here. I kind of went over this a lot in the last video, and this is exactly what I did here. Okay, back to the code. No, this is not better. Okay. Alright, so this is for a floppy. We want to install stage 1 with no offset. So basically, we want to install stage 1 right exactly here in the first sector. And for stage 2, the offset is set to 1 because we want to install it here, starting from sector 1 in that reserved area that we created, that we specified in this create file system. Okay, the next step is to copy the files, and basically I'm starting by copying the kernel. So for the kernel, mmd, I'm using mtools again and calling it using this sh library. So mmd creates a directory which is called boot, and then we are copying inside the image, we are copying the kernel into this boot directory. And then we are copying the rest of the files. Here in this section, I'm trying to figure out the path where the file will be stored on the disk. This is what file dst is. File rel is basically the disk relative to this base directory. And I think, yes, I pass it here. Because from the image, this root directory is basically the root where all the files that I want to copy to the disk are. And I'm passing this to the build floppy command. Okay, now I'm going through every file in this list. If it is a directory, I'm just gonna create that destination directory. If it is a file, then I need to copy it. Okay, so this is how we create the floppy image. Now, the disk image is a bit more complicated, and let's see how we can do that. Okay, so starting from the beginning. Okay, now the size of the disk image is going to be passed through an argument it's coming from this environment variable, from this environment command line argument, whatever you want to call it. All right. And I'm basically rounding this up to the sector size, to the next sector size. Okay, then I'm just storing the file system, and this will be where the offset for the first partition is. So this is the sector where partition 1 will be stored. Okay, same as before, we generate the image file. This will generate an empty file, which is full of zeros, that has the exact size that our disk image will be. Then we create the partition table. As I mentioned before, to create the partition table, build disk. All right. To create the partition table, I'm using the parted library. This is the library, Python library. You can also install it through the pip package manager. Okay, so it just offers us a bit of a nicer interface to work with instead of just calling the commands directly. Okay, so what we want is we are getting this device from this file. This is kind of how parted works. Fresh disk will create a new partition table. So here we can specify MS-DOS or we can specify GPT, but GPT is a bit of a different topic. GPT is mainly used for UEFI. Theoretically, you can use GPT with one of those, you know, MBR bootloaders, but it's... why? Nah, it's not gonna work that well, and I'm not sure if even Grob recognizes that combination. It's a strange combination. Okay. Then we are trying to determine how much free space there is. So instead of passing the size and subtracting... Okay, I'm just gonna get free space regions. So we just want to fill the entire disk with this partition. Okay, and now we are taking this free space that Parted has returned to us, and we are just taking the end, and we are using our own start. So basically, instead of whatever value this will return, our partition will start at sector what did I do? Our partition will start at sector 2048, this one here. And it will end at the maximum... It will end well where the file ends, basically. Okay, then we are creating the partition. This is gonna be a normal partition. In parted terms, a normal partition is basically a primary partition, because this is something else about this MBR scheme. Inside this partition table, you don't have a lot of partitions. You have 4. That's it. You have 4 partitions. And this is why whenever you're using a utility to create partitions in MBR, you have 2 types of partitions. You have primary and secondary or extended partitions, because here you can only declare 4. And if you want more partitions, then you will need to have a workaround, basically. And the workaround is that this table, you know, the entry in this table will not point to a partition, but it will point to another partition table which has more partitions. And that's it. Okay, then we are setting the boot flag. This is so that MBR, this code here, this code which exists here in this MBR, so it knows that which partition to load from. Okay, then we add the partition to the disk and we commit, which will write all the changes to the disk. All right, let's continue with mount FS. And this is a really cool thing that I have found. if you remember from 2 weeks ago when I did the live stream, the way I implemented this was by actually mounting the disk. So here we are using, where was it? I've seen it for a second and it disappeared. Okay, so we are using low setup to here. We are using low setup to create, basically to attach the disk, and so we can see all the partitions inside that disk. And to call a low setup, you need root access, you need administrator privileges. So this is something really inconvenient. Also, we also did a mount somewhere here. Yes, we just used the mount to mount the actual disk image, which is, again, is very inconvenient. And I found a better way of doing this. But the problem with the way that I have here is that it's not 100% portable, even between distributions of Linux. In some distros, this is really easy to do. In Fedora that I'm using, it's very, very easy to set up. But in other distros, it might be more complicated. And I don't think it's gonna work on Mac. But I haven't tested it, so I think it's not gonna work, but whatever. Okay, so let's see how I did it. Using the mount, the guest mount command. Guest mount is a really cool command, which you can install, for example, on Fedora using the package manager. So just dnf install guest mount. Yes, I want to get to the FAT32 part of the stream too, but I feel like I really need to explain this, and this is my chance to do it. In Ubuntu it may be, I don't know, apt get, and I don't know exactly. I haven't tested this on other distros yet. Okay, so I'm using guest mount to mount this image to a directory, and then on mount it's just calling fuser mount. -u, it's used to unmount it. Okay, so let's see if I have everything. I don't see any of those squiggly lines, which means that I think I copied everything. Okay. Now, something that would be really cool would be to have this script detect if guest mount is present, and if it is present, to use it. And if it is not present, to fall back to using mount, and the rest of the other stuff. It would be cool to have this auto detect and to work properly on any distro, whether you have guest mount or not, whether you have, I don't know, whether you're using Mac or... yeah, it takes a lot of time to explain all this stuff, I agree. Okay, so moment of truth. Let's see if all the changes that I made here work. Okay, let's see if I embarrass myself or not. Okay, something did not work. Okay, I know what the problem is, and I had this issue before. Scons doesn't like the fact that in our kernel we have a bunch of files, and we have a bunch of C files and a bunch of assembly files have the same name, idt.asm and idt.c, because both of these will result in idt.o. And Scons doesn't know how to deal with that. So the easiest way to fix this is to just rename one of them. So I don't know, adt.asm.asm. It sounds weird, but at least we will fix the issue. isr asm.asm. Okay, and there are a couple of things I haven't done yet. Okay, GDT. Yeah, so it's not the only one. Where are you, GDT? Here you are. Missed it. Okay. And it's almost working. I think it might actually work. Mounting and unmounting takes a bit of time. And everything looks good so far. Okay, there's some errors in the... Okay, this is something that we have to fix. This will be an easy fix. And uninitialized space declared in non-BSS section. Okay, we will see. Okay, we will see in just a moment what that means. Okay, so the first issue is in the boot in stage 1. Because I have this entry symbol here, but I haven't made it global, so that it can be seen by make, and it can not make by the linker. And I don't know what this is about. Uninitialized space, boot ASM line 18. What do we have at line 18? Oh, okay, so I have this RESB. RESB is uninitialized space, which is usually stored in that BSS section. So it doesn't like doing that. You can do it, but it's not gonna be a fan of it. So let's just put this back the way it was. A, B, C, D, E, F, G, H. That's 8 characters. Alright. And I think everything works, which is amazing. Now, using these guest mount is a bit slower than I think using mount would be slow too. I'm not really sure. Yeah, and there was something else that I wanted to show you here in this image Scons script. This is not the prettiest. I'm not very proud of this line of code here, but I've encountered that right after copying all the files to this mounted file, to this mounted disk, basically, this would give an error like a disk is busy or something like that. And the simplest way to fix that is just use sleep. Now we could find a better way, like, I don't know, trying this command again if it fails, or I don't know, a couple of times, but it's fine as long as it works. And yeah, that's basically it. So now we have this image. There are a couple of things we are missing. Okay, let's do some cleanup around here. We no longer need these. We don't need this. We don't need... we kind of do need this one, but we will just create a new one in this build scripts folder. We don't need the makefile. We don't need these. You don't need these. Delete. This is so satisfying. Deleting stuff is my favorite. I really love deleting code. Even at work, I'm really a fan when my boss asks me to, okay, now we are deleting this feature that we are not using anymore, that's deprecated. I'm very happy. I don't know why, but deleting stuff makes me very happy. We don't need this makefile anymore. We don't need this makefile anymore. And in this build script, we don't need this anymore. We don't need... Okay, something I haven't done yet, and this is something that I wanted to mention, is I had this piece of code which was generated using this shell script, generate isrs.sh. I haven't written this yet, and I don't think it's worth spending the time to do this in this live stream. I will do it maybe offline and just show you what I did when it's done. So this is one of the things I haven't done yet. I don't need these. I do need these. and the stored chain.make, I have replaced it with a shell script. Maybe it's not... It's fine. Alright, and now let's see what I am missing here. Come on, where are those? Okay, so I did not create them in... I created a separate folder. I created a scripts folder. Wait, these are specific to the build, but these are not. These are just other scripts that do other interesting things. Okay, and the first one is that the run script. Let's create that. So run.sh. Okay, we're running this with bash, and we're basically going to generate the camo command here on the fly. So the way this is used from this main Scons struct, which is this one. Okay, so we have these 4 only targets. We are calling run.sh from the scripts directory using the image. Okay, this is the image type, so it's either floppy or disk, and then we are passing the path to the image file itself. So it has 2 arguments. All of these commands actually look identical. They have 2 arguments, the image type and the path. And in run.sh, this is exactly what we're doing. We have these camo args, so we are using 32 megs of RAM, which is not a lot, but it's fine for the moment. And if the image type is a floppy, we use -fda. If it is a disk, then we use -hda. And then we just call the camo command. Okay, for debug, after my issues that I had in the previous live stream with box, I kind of decided to put it like, to not have it as the main debug tool, to use camo for debugging as much as possible, because camo is much better, to be honest. Box is kind of old, and some things don't work the way they should. I don't know why, and honestly, if some of them may be fixed, I don't know. But if box doesn't work properly, then we just demote it and not use it as the main debug tool. Okay, for debug, I have a pretty similar script in debug.sh, and in addition to what arguments we had here, I added this -s, which means that hey, we want a debugger, and -gdb, we want the debugger to be gdb, and we want to debug through stdio. And the way this works is that we have this gdb script. We are basically just generating this file on the fly, and then calling gdb using this file, and then deleting the file. And yeah, this is the same as in the other file. These commands, this is basically gonna set the breakpoint in the boot sector. This is going to show us the assembly code, and this is the command that we actually need to run camo and gdb together, basically, to run them together. Okay, now for box.sh, this file is kind of similar to the other ones as well. Now the syntax here is a bit different. We have this box config file, and same as we did with that debug file. Yeah, we generate this on the fly, and then call box using this file, this config file. Okay. In addition to the scripts, I have created a little script here that I'm going to install deps, but it's kind of not really ready for prime time. I kind of tried to do something to make this easier to set up all the build environment by basically detecting what package manager is being used, and then just calling the right command using the right list of our dependencies. And this is what the script does. It's not super well. I haven't tested it. I have tested it on basically Fedora and OpenSUSE because I use OpenSUSE on some server, but I haven't really tested it very well. But I'm leaving this here. Yes, Alpine uses APK, but I don't have the list of APK dependencies, unfortunately, because I don't know what they are. I haven't really done that much research. I do have the list of dependencies from Arch, and I took these from the README file because I had these lists here, and that's why I have this. And in addition to these, I also added these Python and Python Scons. Now, some things are missing. The sh library and the parted library that I used in Python, these are missing. Yeah, I will have to test the script a lot more before I'm ready to write about it in README, basically, to let everybody use it. Okay. Okay, let me see if I have anything else. Okay, so the setup toolchain. I deleted that make file that for building the toolchain, and all I have is this setup toolchain.sh, and all I have here is just basically the same code but in a shell script instead of make file format. Now something I'd like to do here maybe in the future is to pass these variables, instead of having them here, to pass them down from sconstruct, because we already have this nice list of dependencies, so why not pass them from here to this setup toolchain? That would be nice, but yeah, another time. I'm not gonna spend too much time on this because I've already have a video about building the toolchain and automating it. I'm not gonna spend any more time here. And yeah, I also added this operation command word so that you can clean. If you want to delete everything from that toolchain directory, you can do that. Okay, now we have finished with the first topic. Okay, there was one more thing that I mentioned that I want to do that I haven't done yet, which was in the image generator, in this install stage 1 function, and I had this to do here, and basically the way I have set up. Okay, let me show you a bit. Here okay, I can put it below. So the way I set up my stage 1 is that, okay, so we have these 3 bytes, which are the jump instruction here. Then we have the file system headers, and then we have the entry point here. Okay, I'm stretching too much. Okay, so we have everything we have here, all the stuff, and then right at the end of stage 1, we have that signature, so AA55, and we have a little array here of basically pairs of the sector and the length. So we basically have an array of, I don't know how many I declared, I don't know, 6 maybe, I can't remember, but we have basically an array of entries that look like this. They have a sector number and a length. And the way we basically install stage 1 is we specify where we can find stage 2. We specify that right here and how long each sector is. Now, this is something that we have to do right now to add here in this install stage 1 code. And I already have most of it here. Okay, let's see. Let's declare a symbol that we can use. Okay, so I have this stage 2 location. I'm gonna make it global. And now if we build this, Scons. All right, we have built stage 1. So too much junk here. I have to clean this up a bit. Stage 1 dot map, and we can find the stage 2 location right here. So again, using the same trick that I used here for the entry start symbol, I'm gonna search for the stage 2 start symbol. If this is none, then we complain, and then we subtract 7000. That's it, really simple. Okay, now we know where that is, and now we need to pass here the information where we can find stage 1. So let's add these as parameters. Stage 1, stage 2 start, and let's have this like, I don't know. Actually, let's put it in with the positional argument. Let's not make it optional. So, and then stage 2 size. And the way this is encoded is that the start is... no, I have a conflict. Okay. Stage 2 offset. Okay, that sounds better. Okay, so I'm writing stage 2 offset 2, and I'm converting this to bytes. This is how we can do this in Python. And we want to convert this to a 32-bit number in Little Endian. And then we write the size in number of sectors, the stage 2 size. And we write that in bytes, because this is what we decided to do last time. And we don't seek to address 480, we have to seek to this stage 2 start. Okay, basically, I think this is it. Yeah, and we also have to take care of this offset, so we have to keep in mind that... Okay, so here, we have to keep in mind where we are. Okay, entry offset multiplied by sector size plus stage 2 start, and we are seeking from the beginning. Seek set means from the beginning. Okay. Right, location of stage 2. Okay, and now let's add these parameters. Stage 2 offset will be 1, and stage 2 sectors equals stage 2 sectors. Alright, and this looks good. And we will need to do the same for the disk image. Install stage 1. And again, we are starting at offset 1, and sector 2 sectors is the size. Okay. Let's see. Scons. Okay, let's clean everything. And I have all this junk left over from when I was using make, so I'm gonna delete everything. Scons. Alright, Stage 2 size, I think. Okay, it wasn't stage 2 sectors, it was stage 2 size. Sorry. And in build floppy as well. Alright, done building target, but it's not up to date. Okay, something's messed up in my dependency tree and I need to figure out what. Installing stage 1, type error, can only concatenate string at... What? Stage 2 in map file. What is this? Did I do something wrong here? I'm using it the same way. So what is wrong? String to string. Where am I concatenating stuff? Oh. Okay, so it couldn't find stage 2 start in the map file, and then it threw this error. And then when I'm creating this value error, okay, I know what is going on. So here I have to use str of map file. So it basically threw an error that it didn't like how I concatenated the stuff. But basically it didn't find the stage 2 underscore start. And let's see why. Stage 1.map. Oh, it's called stage 2 location. That's why. Okay. Scons clean and scons. And this looks good. Yes, we have an image. Okay, let's see if permission denied. Oh, I have to do chmod plus x to all the files in build in scripts, not build scripts. Okay, I think this should work. And again, we have this error that we had in the previous live stream about because we are trying to use FAT32 and we don't support it. Okay, so 2 hours of live streaming. Yeah, that's a lot. Okay. There's one more. Okay, let's commit this because these are a lot of changes and. Okay, Scons light, db light, I add this to git ignore. Yes, I want to delete all of those files. And I want to add the bycache directories to git ignore as well. So, underscore, underscore, bycache, underscore, underscore. Okay. Let's see what we have here. I think this looks pretty good. I don't see any more problems. Okay, let's commit this because this was a lot of work. Changed build system to Scons. All right, and yes. And let's synchronize these changes and push them to. All right. So now let's talk about. Okay. I don't want to make this unpleasant, but I want to do something really cool about how we implement this FAT32 support. Because right now we already have a driver that supports FAT12. And it would be a shame if we made some changes which broke the support for FAT12. So Anyone who has been in the industry knows about automated tests. And the idea here is that whenever you are making a change, like what we're doing right here, you have to test every possible scenario. Every time you make a couple of changes, maybe you break the support for FAT12, so now you have to test FAT12, you have to test FAT16, you have to test FAT32, and you have to test so many scenarios, like, I don't know, long file names, what other scenarios, large files, small files, empty files. What if something is corrupted and you want to test how well your code works with that? There are a lot of scenarios, and covering them manually is going to take a lot of time. And this is why in the industry, a lot of people are, and most companies are using automated tests. And these make your life easier, but they are also hard to write because you have to, you have to have good tests and you have to run them periodically. Maybe some tests may take a long of time to run, and there are all kinds of types of tests. There are stress tests where you are trying to make it break by, I don't know, for example, creating and deleting files and moving and renaming and all that, and doing that for like an hour and seeing if anything breaks. If you reach some, I don't know, compilation issue or some limit or something you haven't thought about. And this is kind of the goal here as well. One of my goals here is to make an operating system which is well tested and which will work great and which is easy to work on and which is easy to build upon. And I think having automated tests will help a lot with that. So now I've been looking around a bit, and there are a couple of framework libraries which can be used for testing, and I decided to not use any of them because they suck. Because none of them is simple enough for us to use in this context. And what the context is in our case is we want to have a way to easily integrate this testing functionality into the kernel, because we may want to do integration tests where we test that everything works together, that, I don't know, our for example, the interrupts get called. This is something that you can actually test if you write automated tests inside the kernel. And I want this library to be very lightweight. Okay, enough talking, so let's get to action and think about how we can design this testing framework a bit. We will not spend a lot of time on it. We will make it very simple. Okay, so inside the source directory, let's create a new folder and call this, I don't know, testing. Okay, testing because it's our testing framework. And let's create a header file inside testing.h. Okay, so what do we need to write tests? Let's think a bit about how we will write a test. Actually, let's start by actually writing a test. So let's create a separate folder for all the automated tests. And I don't know, let's create a main.c or cpp. Should I do C or CPP? Stream, please tell me. Guys, please tell me, C or CPP, what do you want? Okay, in the meantime, I will create a Scons script file for this as well. C, okay, somebody voted C. Okay, it's gonna be a C file. Okay, and this will be a normal, just a normal program. Okay, and let's use, I don't know, stdi, no, I mean C, I forgot, std io.c.h, and okay, so let's create a suite of tests for the FAT driver. Another thing here is we're gonna want to, right now we kind of have the FAT driver in the kernel, and we also have it in stage 2, which is not very cool. A lot of people are saying C. Come on guys, I want to use C++ for once. Okay, I just committed, Andre. If you haven't paid attention, I have just committed. Oh, the debug log code. I haven't done it yet. I'm sorry. I have released this video recently about writing debug logs, and I haven't committed the code yet. I'm sorry. I will do that. I promise. After this live stream. Okay, so let's create a new folder called libs, and this will contain our libraries. And the first library will be, I don't know, libfat. Does this sound like a good name? And this will be where we will put the FAT implementation. Now, right now I'm just kind of thinking how to do it, and I haven't really... Okay. We will need a Scons script for this as well. But for the moment, let's just not worry about that for the moment. Okay, so inside main.c, we want to test the FAT driver. So let's create a I don't know, a folder. I think a folder is libfat. And let's create a, I don't know, FAT12 tests.c. And we need a header and a C file. All right. Okay, pragma once, so, and now we will just define our test. So let's say that we want to test, just to do a smoke test, to make sure that we have a disk which contains a file, and we want to read that file and make sure that it works. So let's call this a FAT12 smoke test. And let's also add the module which is libfat, so we can yeah, so this looks a bit better. Okay, I'm not gonna write the implementation in the header file because that's usually a bad idea. Okay, whatever, I don't care. And this will contain the implementation. Okay, and for the smoke test, let's think about what we need to do here. So we will probably need to have like a disk image generated for us. We will probably do it maybe in the Scons script, or maybe... okay, but what I want to do here in testing is, so the simplest way to write automated tests is using the asserts. So include assert.h. And now, I don't know, we do something here with the FAT library. For example, okay, for now, let's just do this the ugly way, but we will fix this eventually. So we are in libfat test, and we want to get to testing.h. So test source testing.h. It's a bit ugly, but it's okay. Yeah, so the normal way you do tests is, and yeah, let me just add the patch code as well. So libs libfat fat.h. All right, and I don't know, let's do a fat initialize here. Let's create like a disk and then do a fat initialize of this disk. Okay, and now we want to check that something is the way we expect it to be. For example, assert that disk dot something is what we expect it to be. Come on, quick fix. Okay, I don't care about this anymore. I'll just leave that error. I don't like it, but I'll leave it. And we can use assert. We can use these asserts. But the thing is, these asserts are not super flexible because you're basically, for example, you don't have a message when you assert something. And usually in all the testing frameworks, you have more specific. So for example, assert that this is equal to this. And then you have a message describing what this is. And this is kind of something that we want to have in our testing library. So let's just create some of this stuff. Yeah, this is the reason why I kind of wanted to use C++ for this, because with C++ we can use exceptions and we can check if the condition is false, and if it is false then we can throw an exception and then catch it inside this main.c and then show, okay, this test failed. And we cannot do this in C, unfortunately. But we can use return, so I guess there is a way. Okay, so let's use some nice defines here that, I don't know, assert equals and value 1 and expected. Okay, I don't we should use some different names. Let's, I don't know, capitalize it or something, because it will conflict with the, I want to have assert like this, condition, and then assert equals. Does this look good? I don't know. Expected, actual, and then a message. And here we will also add a message. And we can add a lot of variations of these. Maybe, I don't know, assert not equals. And we can add a lot of variation about to this as well. And of course these macros will have to call something, so let's create a function or something for it to call. And of course we will need testing.c as well, unfortunately. Yeah, another reason I wanted to use C++ is because you can have header-only libraries by using templates, which is very cool, I think. You can do this like this. But anyway, let's okay, so what does this do? Let's think about. Okay, so let's define a function like, okay, so for the assert we will want to exit from the executing function. But you know, this is kind of the main problem, because if we just use like return, I don't know, we will call something like if not condition, we want to return, for example. So this is what the assert macro will look like. But if we are in a child function, so if this function calls another function which has asserts, then it will not work. It will not return all the way to where our main test runner is. So this is why I want to use C++ for this. I'm sorry guys, I'll just switch to C++. I'm really sorry. I know some of you don't like it, but I'm just gonna use C++. Okay? Please don't be mad. Okay. But, damn it. this will not work in our kernel, because in our kernel we won't have exceptions. That's... yeah, in our kernel we don't have exceptions. So I cannot implement my idea. So we have to find a way for these asserts to basically end up here in main. Any ideas? Go to. Go to is a great idea. What else can we do? Because we cannot use throw, because in our operating system we won't have the runtime. Even if we use C++ in our operating system, we still won't have exceptions. So let's look it up online. C. Mind stack or something like that. Not in C++. Okay, this is probably a lot more complicated than... Okay. I do have an idea, which I could use here, but it will not work for the operating system either. We could basically create a thread for each test. Whenever we run one test, we could create a thread. And then whenever we get an error, we kill the thread. Or we could just use whatever assert does and just stop the entire program, and that's it. Yeah, that's probably the easiest way. So instead of returning, we just do exit and throw that and say that, okay, this did not work. I think that would be probably the easiest way. Okay, I will think about this more. I did not think it would be this complicated, and I kind of want to move forward a bit with the FAT32 stuff. And I also wanted to integrate this testing, but it will take a lot of time, so... okay, I'm going to skip that. I'm going to not do this testing stuff this time. And I'm just gonna focus on adding the support for FAT32. Is that okay? And I will kind of think about how to design this better in a future live stream. I thought that this would be easier. I really thought this would be a lot easier. But basically, we have two choices. We could either do whatever assert is doing, which is basically stopping everything from running when the test fails. Which is maybe not ideal. Oh, I have another idea. Okay, I'm thinking about doing something that kind of I've seen in some of the testing frameworks, where instead of using like assert, which kills the whole process, they do something like this. So define test, and then you have to put your code inside this test macro. So for example, if I have this, I would have to do test and define the test inside the macro. Now this doesn't look super nice. Okay, maybe just not even have, okay, like this. I think this might actually work pretty well. And what I'm thinking of is to setting a special return value, basically. So this macro will create a test that kind of looks like this. I don't know, int test function. Okay, so if I run the test macro using test function, or I don't know, whatever, camel case, okay, snake case, okay, with no arguments, and okay, this is still doesn't solve the problem that I was thinking about. And you know, having these asserts basically return something like a -1. So if the assert fails, then we call something like return -1. And then when we write a test function that calls another test function, then we would have to do something like test other test function. It would do kind of like this. So if test function smaller than 0, then return -1 or something like that. And having the asserts use basically the return value. This might actually work. Okay. Yeah, I will think about this more over until the next live stream, which will be on Friday, and I will come up with a better design and we'll show you what I came up with. Okay, that sounds good. And we will talk more about automated testing. And for now, let's focus on adding support for FAT32. Okay, and let's see, we are at 2 hours 26. It's 11. Okay, I'm staying at 1 more hour, and that's it. This has been a pretty long stream already. Yeah, I'm gonna end the stream at midnight. However far we get is however far we get. And we will continue on Friday. Okay, so FAT32. Let's actually look at a bit how these file structures are. So OS dev file allocation table, or FAT. Okay, so we know about FAT12 and we already implemented it. Now let's see what we need to do to support FAT16. All right. Okay, so for FAT12 and FAT16, the boot sector looks pretty much identical, I think. I don't really know if there's any difference. All right. Okay. And then these fields only exist when we use FAT32. All right. These extra things. Okay. Then on FAT32 we also have this FS info structure. All right. And okay, I'm not doing exFAT for the moment. Okay, and in FAT12, basically the clusters are 12 bits in size, and that was the main catch about this. In FAT16, this is a bit nicer. We don't have this ugly 12-bit stuff. We basically have the 16-bit stuff, like this. Okay. All right, so let's start by going into the code. And okay, I will think about this later. And let's go into stage 2 for the moment. And okay, so let's go into this config and set the image file system to FAT16. let's start with FAT16 and try to get this working. And then we will also look at FAT32. That sounds good. All right, so let's build an image using FAT16. Okay, so if that's the only difference between FAT12 and FAT16, then that should be very easy to do. Okay, now the main catch here is how can we detect whether we are using FAT12, FAT16 or FAT32? That's going to be the main challenge. Let's try to find some ideas and discover this together. All right, here we go. We get the formula. Actually, no, this is not. No, this is something else. This is how large the actual file allocation table is. It's not what I thought it would be. Okay, how do we detect this thing? Okay, here we go. So, mainly we use this total clusters, which would be basically how big the drive is. So if the drive is small, then we are most likely using FAT12. If the drive is a little bit bigger, we're probably using FAT16. And otherwise, we're probably using FAT32. But this detection isn't super well. It doesn't work super well because if you use a non-default cluster size, then this will not work. Actually, it might work. Okay. Let's give this a try and see what happens. So the first thing that is going to be different is the size of that file allocation table. All right. Okay, I'm kind of remembering right now how I implemented this. So, okay. All right. Something we will have a problem with is the fact that we are reading this file allocation table completely into memory. And on FAT32, that might actually be kind of large and may not fit in the... because... actually, I don't know. I think it might fit. Okay. In theory, it could get pretty large, but in practice, I think this might be fine because this is 32-bit, so we probably do have enough space. Okay, so let's start by implementing this detection, trying to figure out the size of the file allocation table, the size of the type of the file system, basically. Alright, and we have this FAT data structure where we store all the information about the currently opened disk and all that stuff. So this is a pretty good place to add actually, I can just use a static variable because this is gonna be kind of small. So static uint 8t fat type. Okay, and let's implement this fat detection. Fat detect. Okay, and we are basically need to look at the boot sector. Which is read in Okay, in G database. I don't think I may not need the disk here, I'm not sure. Okay, I don't need the disk. Okay, so if let's see what they did here. Okay, so they're basically calculating the number of clusters, which is the size of the data section. So if you remember from when I made that video about reading the file allocation table, let me jog your memory a bit. Okay. The way the file allocation, the FAT file system is laid out is like this. So we start with the boot sector here. Okay, then we have those reserved sectors. Okay. Then after those reserved sectors, we have the file allocation tables, and there are 2 of them. Okay, this is not visible. Okay. The highlight is... okay, now this is better. So, here we have the... as I was saying, we start with the boot sector, then we have that region of reserved sectors, we don't care about that. Then we have the file allocation tables, we have 2 of them. So there is FAT1 and there is FAT2. Okay, and then we have the root directory, so let's call this RD. And, okay, this is an ellipsis, so this is the continuation. Okay, and then here we have the data section. This is called the data section. Okay, so what they are doing here is the total number of clusters, which means how much space we can basically use for storing data, is the size of this region minus divided by the number of sectors per cluster. Okay, and depending on that, so if it is smaller than 4085, then that means we are using FAT12. If it is smaller than 65,525, then that means we are using FAT16, and in all the other cases we are using FAT32. Okay, so let's kind of implement that. Now I'm not really happy with this mechanism they are using for detecting. I don't think this will work in all cases. I can't think of a case where it won't work. I mean, for starters, we are specifying the file system manually here. In this image, I basically in this disk image that I'm creating here, I basically just we pick this at compile time. We pick which file allocation table version to use. So I don't think this will work very well. But I can't think of a better one at the moment. But okay, let me check. It all boils down to what are the differences between these things here. What are the differences between FAT12, FAT16 and FAT32? And we've already seen that in FAT32 some of these fields are 0. For example, this number of sectors per FAT is 0 in FAT32, so that is a very reliable way of detecting whether this is FAT32 or not, whether we have or not this set to 0. Other than that, there's this where was it? This one, this system identifier string. But the spec says to never to trust the content of this string for any use, so that's not very useful. What else can we do to detect whether it's FAT16 or FAT12 or FAT32? Yeah, so this is the best we have. If this field is set to 0, then that means that we are using FAT32, absolutely. If the number of sectors per FAT is 0, I think we might have to rely on this untrustworthy value here. Or just do the cluster stuff, because realistically you're not going to use FAT12 for any kind of disk except for the floppy. So I think that might be fine. Okay. In that case, it is decided. I'm going to use this detection they use here for FAT16 and FAT12 and FAT16, but for FAT32, I am going to just see if that size is 0. Wait, so if sector size is 0, then the FAT type is XFAT. Oh, okay. This is interesting because in XFAT they're basically dumping all of these fields. They're not using any of them. They are just setting everything to 0, and they are defining new fields starting from address 64. That's basically how XFAT works. Unfortunately, this leaves us with a lot less space for the boot sector. But yeah, whatever. That's how it works. All right, so we need to determine the number of clusters in the data section, and the size of the data section. We have this here. Is the total number of sectors from which we subtract the number of reserved sectors, and then the size of the FAT, and then the size of the root directory. All right, so we cannot do the detection this early. We have to calculate all these sizes first. Okay, so data section LBA is here. Okay, what are we doing here? We are reading the boot sector, then we are reading the file allocation table, which is probably okay because we are using this number of reserved sectors. Okay. No, what did I do? I got confused. It's okay. Okay, so then we are reading the FAT, then we are calculating how big the root directory is by basically doing all that calculation. And then we are basically reading that root directory. Okay, and then we are calculating where that data section is. Okay, what I think I'm gonna do is move these up. Reading the file allocation table is probably fine. And the root directory. Okay, let's see. Okay, I think most of these things will work, basically, including this. This will also work. Is there any difference in... Okay, so I think there is a difference between FAT32 and FAT16 in terms of the file entries. So the size of a file entry might be no, it's not different. So they all use the same format for the file entries. Okay. Okay, we are ready to implement this. Okay, let's keep the documentation near because we will definitely need it. Okay, so I think this will actually work to get the position of the root directory and to get the size of the root directory, because it's all about the fields from this boot sector. We have the number of root directory sectors. We have the number of root entry count, actually this root entry count, which gives us the number of entries in the root directory. So this will work fine. Everything up till this point should work fine, including calculating the data section. But opening the file, that's the part that will not work. Okay, so let me check a bit. Let's say if I run Scons run, let's see what Scons run has to say. Okay, not enough memory to read the file allocation table, required a lot, but only have 65k. Okay, that might actually be a bit of a problem. But why is the file allocation table this large? That doesn't make much sense. So, okay, maybe something here is off. All right, so we are reading the boot sector. And then we are reading the FAT, and the FAT size is the number of bytes per sector. Okay. Yes, the number of bytes per sector multiplied by the number of sectors per FAT. Okay, let's print what we're getting here because something is odd. Okay, let's print. And yeah, maybe something is wrong with the way we generate the image, and because it's not that well tested. Could be, we don't know. Although if there was something wrong with the way we tried the image, then we wouldn't be able to mount it, basically, because that would create errors. Okay. Okay, let's see if this helps. Okay, so the number of bytes per sector is odd. Because the number of bytes per sector, I would expect it to be 512, basically. Why is it different? Something is definitely off with this image. Okay, let's go and... Okay, so the boot sector, nothing should go wrong here. Oh, I know what's wrong. I know what's wrong here. We are trying to read the boot sector, but remember that here we are not on a file system. Here we are on that MBR. So this is not the file system. This is not the partition. This is the master boot record. Yeah, that's the problem. So we need to figure this out. We need to basically parse the master boot record, and then we will be able to read the file allocation table, and we will be able to adapt this code. Okay, so let's create mbr.c and mbr.h. mbr.h and mbr.c. Okay, and let's create a function which does the detection, basically. MBR detect partition. All right, and this one should return basically the partition start. And this one will return uint32. And we want a disk here because we are using that disk.h. Okay. Okay, now we had this we have to get some memory. Let's see what we can use. Since I think we can reuse this memory FAT address because we are going to initialize the FAT driver after we detect the MBR stuff. Okay, so okay, let's read the boot sector. Let's read the first sector. Disk read. I have to include mbr.h. Okay, okay, and what we can do here is the BIOS passes us this disk ID, and we can kind of use a trick here. If the ID is 0, then we know it's not a disk. We know it's a floppy disk. And if the ID is greater than 80 in hexadecimal, so if this is okay, so if this is smaller than 80, we will just return 0 because the partition starts at 0. And else, okay, I wonder, we have to look at the structure of the master boot record. Okay, and the way this works is okay. Wait a second. Because I think... Oh, okay. So the MBR does something that I forgot about. And this is what I was reading here. So the master boot record, which is that little bootloader which exists right at the beginning of a partitioned disk, it does a couple of things. You know, the things that we would expect. So it searches for the first active partition, the first one which has that boot flag, and then it relocates itself to another address. It determines what partition it finds that partition basically, and then it okay, it loads the first sector of that partition, which would be that volume boot record. This is how it's called here. And then it sets the SSI to the selected partition table entry. And I wonder if this will leave that entry in memory, because this is something I'm very curious about. If the SSI will point to... I think it might actually do that. It might leave it into the... Okay. Let's see if... I don't see this mentioned anywhere else. Okay. Okay. So this is really cool. So the MBR bootstrap, which is basically there, it will give us in this DSSI pointer, it will give us the address of where that boot sector is, which is cool because we can use that information and we don't have to read the boot sector again, we don't have to parse it again. So we have to, that's basically what we have to do here, is just use that part. Okay, so what we can do here is in this detection code is if so in stage 1, we basically need to make sure that DSSI is set to 0 or something like that, to an invalid value, like 0 is a good option. Okay, let's see if we can do that. So DS is already set to 0 because we are booting from 7C00. This okay, so what we would have to do here is, in addition to, in stage 1 basically, in addition to okay, so we are saving the drive number in DL. And we should also save whatever value is in SI, because that will contain the location of the partition entry. Okay, so let's save that as well. I can create a variable here in this data section. And SI, okay, it's a word. DW0, and we will store whatever we have in SI, we will store it into this variable. And when we jump to stage 2, which would be, where is it? Here. Okay, so here we load the drive number in DL. Let's also load the boot partition in SI. Okay, and now let's go into stage 2 entry. And here we also need to save this value because we don't want to lose it. Okay, so G boot partition will be a word, and where did I save it? Here. Okay, so we will save it into this variable, and then when we jump to the kernel, when we jump to the C code, sorry, we will want to push that as well. Okay, okay, we have to push them in reverse order, so let's move into... Okay, so right now we are in 32-bit mode, so whatever we push, it has to be 32-bit. Okay, we can use DX in that case. G boot partition, push DX, push EDX in fact. Okay, something that I was thinking about here is that here in stage 1, okay, so the article, you know, the OS Dev wiki, it says that it's DSSI, so DS may not be 0. That's something that I'm thinking about here. And if DS is not 0, then we also want to save DS. Okay, so right before setting up the data segments, okay, let's save it to the stack. I think that actually might be a good idea. Let me think. So we basically want to save whatever is in DS. Okay, we can just use some other register. So save DS, which contain segment of boot partition. So let's just save it to DI, for example. That should be fine. Okay. So we will save both the boot partition segment and boot partition offset. Okay, and then we will save whatever is in DI as the segment. Okay. Okay, so this looks pretty good. So we are saving DS here, and we're storing it temporarily in DI, and then a bit lower we are putting that into the memory after we've initialized our data segment, because otherwise this move will not work without having initialized the data segment. If DS is not 0, then this will not work properly. Okay, then we set up the stack and then the rest. Okay, this looks pretty good. Here, when we jump to stage 2, in this case, we will also want to... Okay, move the segment, then put that into DS, so move DS. Actually, we don't have to use DS. Do we have to use DS? Okay, let's just keep things consistent here. Okay, fine. I will just use SI. So SI and DI for the okay. So SI will contain the offset and DI will contain the segment. And now we go to stage 2. Okay, here we are going to save these two numbers to the boot partition segment and offset. Okay, the SI was the boot partition offset and DI was the segment. Okay, and now we go to this code here, where we want to set the address of this boot partition. And it would be nice if instead of passing the segment and the offset, to pass the address already calculated. So let's do that. It's gonna be pretty easy. Okay, so let's put into dx the segment, and then to convert from segment and offset to a linear address, all we have to do is multiply the segment by 16. So shift to the left edx, we will shift it by 4 positions, and then we will add to dx the offset, and now we have a very nice address. Okay, this segment and offset, okay, so here we might get a little bit of I'm thinking. Okay, so here let's use some other registers. Let's use for example CX, so XOR EAX. We are going to set EAX to 0. Is there anything in EAX that needs to be preserved? I don't think so. Okay, so this offset is a 16-bit number, and we want to convert it to a 32-bit number, right? So what we do is we just put it into AX and set the upper half of AX to 0, basically. This is what I'm doing here, and then we can do add EDX EAX. Okay. And now we have this value converted. Although, I don't know if this matters as much. It might be nicer to do this in C. It will look a lot better. This code is ugly. Okay, let's do it in C then. I changed my mind a lot. Okay, so we are gonna put into dx the segment. Then we are going to shift everything to, we are going to shift edx to the left by 16. So now this segment is in the upper half of edx. Now we are putting into dx the offset. And then we are pushing this. Okay, so boot drive in the okay, and now for the boot drive, we also need to clear the EDX register, set it to 0, and then push it. Okay, so now we have two arguments in the start method. The first one is the boot drive, and then okay, and this will be the partition. Okay, so we will okay. Okay, before we initialize the FAT driver, we will need to do that MBR detection. So, int 632, okay, partition start equals detect MBR. I haven't included mbr.h. MBR detect partition start of this disk, and we're also gonna pass this address. Okay. And okay, so now again, if the disk ID is smaller than 80, we are going to assume that this is the floppy disk, so it is not partitioned. Otherwise, we are going to look at this partition and try to figure out where it starts. Okay, so let's see what these table entries look like. Okay, so we're basically looking at LBA of partition start. This is what we're interested in. We don't care about the CHS address, all we care about is the LBA. Okay, so it is at offset 8. But still, it would be nice to create a structure for this. And okay, MBR entry. Okay, so first we have UN int 8 attributes, then 3 bytes for the CHS address, so uint 8 of CHS address of 3, then the partition type, okay, then another pair of 3 bytes for the last partition sector. Okay, and then LBA of partition start. This is what we are interested in. LBA start, and then the number of sectors in that partition, so basically the size. Size. Okay. Okay, so now we need to convert this into a normal address, into a 32-bit address. I think I had some macros somewhere where I did that, but I don't remember. x86 here, is it? No. Come on, I think I had some macros defined somewhere where I do exactly this. I don't, I'm surprised. I absolutely remember having some macros about this. Okay. Okay, we don't have, so... Okay, let's go to memory.h and let's do this here. And have a function to convert void seg offset to linear. Okay, this sounds good. Segment and offset to linear of an address. All right. And to make this conversion, basically the lower... okay, so we have to extract the offset and the segment. The offset is the lower half of this address. So we are casting this to uint32 of address. And just taking the lower 8 bits. No, the lower 16 bits. And then for the segment, we have to shift to the right by 16 bits. Okay, and return segment times 16 plus offset. And let's cast that to a void. Actually, I think I can leave these as uint32, so I don't have to do another cast. I think that should be fine. It's not a problem, because I'm basically removing the upper part here, and here I'm shifting to the right, so it should be fine. So I don't have to add more casts here. Okay, good. Include memory.h. And let's just cast everything to the entry, which would be seg offset to linear of partition, cast to an MBR entry. And let's print everything we get here and see if this works. Include stdio. And let's print flags, attributes, whatever, attributes. I don't care about the CHS stuff. Let's print the LBA start and the size. All right, and okay, we are just gonna return entry LBA start. Oh, but we should also return the partition size. I think that might actually be a very good idea. Because we will need that to calculate that data size. All right, we will see what we have to do, but now let's run this. Okay, so in mbr.main.c, okay, we have to use the address of disk. Okay, let's see what we get. I forgot about the \r. Because we are in... Okay, anyway. So, attributes 8 and 4. And it said here that bit 7 means active or bootable. So we have the 8, which means that this is bootable, which kind of indicates that we might. But the LB start. Oh, I forgot to do something. We have to pack this structure. Okay, let's get one of those attribute packed, because we have this we have these 3-byte stuff which will not play nicely. Okay, let's see. It didn't build the image. Yeah, and let's do the backslash. The new lines. Okay. This still doesn't look good. I'm not sure if... I don't think this is correct. Because the LB start, it should not be 8B2FEB00. That doesn't look right. It should be... I wonder what went wrong. Okay, I think it might be a good idea to use the debugger for this, because this doesn't look right. The LB start of this partition, it should be 2048, or some, I mean, I'm putting here in hexadecimal, so it should be, I don't know, a round number. But this is not a round number, so something is definitely wrong here. And I think we should debug. So, Scons, debug. Okay. Okay, let me just use a normal terminal for this. Okay. And let's continue. Okay, this is going to be the code for, by the way, can, hold on a second, I have to fix something. GDB, Intel ASM. Yay, we can do this. This is awesome. So let's set this assembly flavor to Intel. Okay, so this should be the master boot record. So I think it's safe to continue. And now we should be seeing the boot sector, I think. Although I am not certain. This doesn't look right to me. Let's go to boot.asm. Okay, so it should start. Yeah, I think it might be fine. Okay, so step instruction. Yes, and the first thing we did was to save DS to EDI. Okay. You want to use AT&T debug syntax? Look, we are using Intel here, okay? Print regs or inforegs. Inforeg. Okay, inforeg. So DS is set to Where is DS? DS is, it was above and I missed it. Info regs. Info reg. Where is DS? I don't see it. Why is it jumping over DS? I don't like this. Info reg. Am I blind? I don't see the DS register. Where is it? Okay. Info reg. I still don't see that. Okay, here it is. So DS is 0. And I think I missed SI. SI is 7BE. Okay, so that's probably where the stuff is. Let's actually dump some memory and see if that makes sense. I think this might be a great idea. Dump memory GDB. Alright, so we have to use X, and how do we do this? X for examine. Alright, XB 7B. Let's see if this works. Alright, okay, so I have to use that slash, and the number is the repeat count, which is defaults to 1, which is fine for me. And X for hexadecimal. Okay, so X slash XB if okay, and the count, how much memory to display? N. Okay, so I have to add X slash, I don't know, 20XB. This syntax is horrible. Whoever invented this syntax is awful. Okay, so 80 is the first bit. Let's see against this table. So okay, this kind of makes sense. Then we have the CHS of the partition start, whatever. Then the partition type, 1 byte. Another CHS thing, and then what's this? Offset. Okay, so 4 and 4. 1, 2, 3, 4, 6, 7, 8. Okay, so this one should be the LBA. 0, 0, 0, 8. Okay, how much is 800 in hexadecimal? Hexadecimal 800. Okay, that still doesn't look right. So why doesn't this look right? ESI. Okay, so ESI is 7BE, and if we dump the memory at 7BE, it looks like this. So this might not work, unfortunately. Or it might be using the CHS, but it shouldn't. In theory, it should work with giving us this LBA partition start. So this is 0800. No, this doesn't look right. So I'm not sure if this is working properly or not. Okay. I want to check the disk in a hex editor. By popular request, I have this IM hex tool, but unfortunately the text is very small and I can barely see it. And you cannot make the text larger. That's something I hate about this thing. Okay, so the image we are using is this one. Nanobyte. Okay, so this is the boot sector, and this should be the information about that partition. So let's look a bit at what we have here. So starting at 1B8, there's the unique disk ID. Okay, so the first partition table entry should be at 1BE. Let's see where it is. This one. All right. And the first partition entry has 80, which makes sense. Then the next 3 bytes are the cylinder head and sector address of partition start. Then 1 byte for the partition type. Okay, and then another 3 bytes for the address of the last partition sector. Okay, so we end up here. And then we have the LBA of partition start, the next 4 bytes. So it was correct. Okay. What the hell? I set this to hexadecimal. 800. Okay, there we go. 2048. I don't know. I'm feeling a bit tired after, spending the last night making that video. Okay, so that means that this is giving us the right address. Okay, next instruction. So let's move on. Info reg DSI, it has 7BE, and that looks correct. Okay, so let's continue. Next instruction. Okay. So now we should be I don't know where the problem is exactly. I have an idea. Let's go. Let's not try to debug line by line because this will take a long time. So let's put a breakpoint at address 500, which is where I load the stage 2, and let's go there and see if the values have been passed correctly. So info regs, this way we can narrow down the problem without having to go through all the debugging. Okay, so the data segment should be 0 and ESI should be 7BE. This looks correct. So it is reaching stage 2, which means that somewhere in stage 2 it gets messed up. Okay. All right, so let's see what we've got here. Let's check the code a bit. Right. Okay, so we are saving the offset in from SI and the segment. Then we are jumping into protected mode, of course. And then we are here. Shift to the left by 16. This should work, but for some reason it's not. I wonder if I inverted these arguments. But I don't think so. Okay, let's go into main and see if I'm getting this the correct value for this. Yes, I am passing this correctly, yay! So that works, but something is wrong here. I don't know what the hell is going on. Alright, so that means that the problem is here in this area here somewhere. So detect partition start. Okay, we are passing that void parameter. Okay, and then we are converting this to a linear address. Are we doing this right? Should be right. Okay, so let's print whatever address we get here. So entry. Do I have yeah. Okay, so the address is correct. Why are the fields wrong? This doesn't make any sense. What the hell? So everything is correct so far. I am getting the right... Oh, I know what is wrong. I figured it out. So, you can see here what the address is. I got it. The address is 7BE, but that we are loading stage 2 starting from address 500. So stage 2 is overriding whatever is being passed there, and that's the problem. And we have to move it. All right, so unfortunately this has to be done in stage 1. We have to move the data from there to some other place. Okay, let's do that in stage 1. So I no longer care about these two. I will just have like a partition segment and then partition up info, what is it called? Partition entry. Okay, partition entry segment and partition entry offset. And let's store them at some other address where it won't conflict with anything. I don't know, 200,000 sounds like a good number. So 200 and okay, so what this will be is the address 20,000 in hexadecimal, whatever that is. I don't know what it is in decimal. Okay, now we know that the size of this entry is 4 plus 4 plus 4 plus 4, so it's 4 times, it's 16 bytes. All right, so we need to go here and move partition entry from the MBR to a different location so we don't overwrite it. Okay, so let's use the extra segment for partition entry segment, but we cannot set ES directly, so move AX the segment and then move ESAX, and then we move DI to the partition entry offset. Okay, we have DSSI, which is already set to. Okay, so we basically need to copy 16 bytes from which is passed through DSSI. That is correct, right? So it is passed through DSSI. Yep. Okay, so the cool thing is that this is already set to DSSI. This is ESDI, so we can use the repetition instruction. So rep set CX to the number of bytes. Okay. Then we need to repeat, but move SB. So repeat move string byte, and let's see if repeat uses CX. I think it does, but let me just check. x86 rep. Okay, so rep stow SB, which is actually move SB, this one. So move CX bytes from DSSI to ESDI. So this is perfect. This is exactly what this instruction does. Okay. And that's it. We don't need to save this anymore because it's a constant. Okay, so we have moved that partition entry, and now when we call into stage 2, all right, right here, all we have to do is set this to partition entry offset and partition entry segment. Okay. Okay, let's see if this fixed the issue. Okay, symbol is not defined, line 75. Yeah, these are no longer necessary. All right, let's see if this works. Okay, so this looks good. This looks good. Attributes 80. This looks good. Looks good. and the size is 7C800, which in let's see how much is that. 7C800. In decimal it is 500 something. 500 something, whatever that is. 500 sectors. Okay, so this is in a sector. So if we multiply by... Okay, let me take this number. I hate this tool. Why is this calculator so bad? So 7C800, yes, it is this number here. Ah, are you kidding me? Why is it doing that? Why cannot I copy this text? Okay, now it worked. Multiplied by 512, which equals 250 megs, and I think that's how big I set this image to be. Let me just see, but I think this looks good. 250 megs. Yay! We got the MBR partition. All right, nice. We're making progress here. Okay, so we are returning the start of the partition, but I think we should also get the... Okay, let's Okay, so what I'm going to do is I'm going to replace this disk for all the Okay, so I'm going to create a structure called type def struct partition, and it will have a disk. Or actually, I think... Okay, let's just use the disk for this. I think it's easier. Okay, so... This is a bit of a hack, but I think it's fine. Win32, okay, partition offset. And then whenever we want to write something or read something, we have to keep this partition offset in mind. And then partition size. Fine, I will not use this. I will make a proper partition. Okay. So let's create a proper partition struct. Type def struct. Partition. And then let's create some functions for this partition stuff. So let's wrap the disk IO stuff. This read sectors function, so partition read sectors, and then we will have a partition instead of a disk, and then the LBA, and then how many sectors. Okay, the rest looks good. And for the implementation, what we will do is just call the disk method. So disk read sectors of the partition's disk. The LBA is LBA plus the offset of the partition, so part plus partition offset, then sectors and lower data. Okay, this will just make it a bit nicer to read and write from a partition without having to worry about where it is. Okay, and detect partition. Okay, let's just call this detect partition instead of detect partition start. And okay, let's have this return like what? Okay, just pass a partition. And a disk. Alright. And what we will do here is set up this partition in equals 0, partition size equals, I don't know if we even have this information, cylinders, heads, and sectors. Okay. The size is probably these multiplied, right? Right? I think it is. Okay, multiplied by heads, multiplied by sectors. I'm not sure if these are 16-bit numbers. Okay, let's just cast everything to uint32. This looks ugly, but else. Okay, so we have to do this, and the partition offset will be the entry will be a start, and the partition size will be entry of size, and that's it. You don't need to return anything. Okay, let's update the code here. And now let's go into main. And yeah, now we have a disk, now we have a partition. Alright, and now when we are interacted with the FAT initialize, we no longer use the disk, but we use the partition. So that's something that we will change everywhere. We're no longer reading from the disk. We are reading from a partition. Okay, and same, I think yes, we need to do the same here. And replace disk.h with mbr.h. Come on, why is it not? Oh, so that's why I made it unhappy. And I think I need std bool as well for the boolean. Okay. What else? What is? Oh. Duplicate variable name. Yeah. Okay. Anything else? Why are you giving me errors? Oh, std int.h. Do I need that? Or why is it complaining? Duplicate parameter name. I don't know. Okay, it worked. Okay, so everywhere we have now the partition instead of the disk. Okay, so now instead of calling disk read sectors, we will call partition read sectors. And this should take care of that offset for the partition. All right. Is there anything that it needs from the disk? Nope. Okay. So now when we run this, we should see the bytes per sector correct and the sectors per fact correct. And we should be able to initialize the FAT driver, but we will not be able to read the file because we're reading the wrong size of the cluster. Alright, compilation errors, wait, hold up. As an argument, one. Okay. So now we have to also, all the functions that we're calling with the disk, now we have to call with the partition. So there's that. That's it? I think so. All right. Come on, read boot sector failed. When you think you make progress and then it turns out you don't. So what is going on? I think I know what might be going on. We're not gonna finish this today, guys. I'm sorry. What I think is happening is, so basically we have to read. Okay, let me check. Okay, so we want to read the boot sector, which will basically mean the first sector of this partition. All right. Now this offset is actually should be fine. Read sector. So why is it failing? I don't understand. This discrete read sectors method is failing for some reason. Okay. Read boot sector failed. FAT init error. Something might be odd about because if you remember from the previous video, from the previous live stream I did, I basically in stage 1 I already implemented this to use the disk extensions, to use the extended functions for reading from the disk, but in stage 2 we don't have that yet. We are still using the CHS functions, basically the CHS BIOS interrupts, and I think that might be the issue here. I'm not 100% certain, but yeah, so basically what is failing is this read boot sector, which should just read that partition offset. Let's see. Discrete sectors. Is there anything wrong with that in particular? So the limit here is, I don't know. In theory, this should be able to read up to 8 gigabytes, which is why this doesn't make sense, because it's just a 250 meg image. So in theory, it should work, but for some reason, it's not working. I wonder if it's these things again, which are always fun. Okay, so let's print this. Read LBA cylinder sector head. Okay, so we are reading LBA 800, cylinder 0 and sector 801. I think that's fine. And then it just says somebody boot sector failed. So why is this failing? I don't understand. Okay, we basically just need to check this function and see what it's doing. Let's run the debugger. Okay, and let's break at, let's look into that map file. Stage2.map and see where this discrete is. So it's at address 2117. So we need to break at 2117. Okay. Continue. Okay, and here we are. So here we are at that discrete function. And of course, what is happening here is we are switching to real mode. Okay. And then at some point we will call the interrupt. And let's see what happens after we return from the interrupt. I don't want it to go into the interrupt, so I'm gonna put a breakpoint at 2168. Okay. Okay, and let's see. Okay, so int 13h. Let's see, read disk sectors. AH should contain the status, so let's print that. Info reg AH is 1, so the status what the hell? What? Oh, what? Bad command passed to driver. What in the world is going on here? This doesn't make any sense. And AL should contain the number of sectors read. So info reg AL 1, but that doesn't help. So info reg EAX. Okay, yeah. Info reg flags. Info a flag. I don't know how to print the flags. Print flags. GDP. Info registers e flags. Okay, and we have carry flag set, which means that there is an error. So it looks like we're not passing the command properly for some reason, which is odd. All right, let's restart. I'm gonna quit and start over. And let's break at 2117. All right, and let's just keep going down. Okay. What am I doing? I'm lost. I am very lost. Let's try again. This happens sometimes. I just move too fast and I lose track of where I am. Okay, so again, 2117 is the address. Continue. Okay, and step instruction. Okay, so we are moving into real mode, and then we are setting up everything. Okay, we have just set AH2 value number 2. Okay, so AL should be the number of sectors to read, which is 1 sector. Then CH should contain the track or cylinder number, so that would be 0. Sector number is in CL, that would be 1. Hold on a second. Sector shouldn't be the sector 801. Yeah, I think this is where it went wrong. Because the sector can only be between 0 and 15. But for some reason our sector is 801. Why is that? That's odd. So what I think might be happening is... Okay, let's print... I think that's the solution, to use the extended functions instead of these. But let's print these anyway. So let's print the disk information that we have. So disk cylinders, disk heads, and disk sectors. CHS. Okay, so disk cells and heads and sectors. Okay, that doesn't look right. The number of cylinders and heads, why is it F000? And the number of sectors, okay, that looks very wrong. So, something went wrong with the detection of that. No idea what. Okay, I think I will end this live stream right now because it's already very late for me, and we will continue on Friday. I will try to figure out what's going on here, and on Friday we will definitely get this done. And I will also look into that testing stuff that I was talking about. Yeah, unfortunately, yeah, when you do stuff live, sometimes it works very well, like it did with the Scons stuff, because I prepared in advance. Sometimes it goes terribly, and this is one of those cases. I'm sorry, but yeah, this is what it is. I was hoping we could get at least the FAT16 drivers to work, but this will take a bit more time. Okay. I will look a bit at the chat. Guys, if you have any questions, I will answer, and then we will end this live stream. It's been very long, and it's already 4 hours long. I always do these long live streams, so yeah, this does not work for me on the first go, so this will... Yeah, so what I think is happening is either I'm getting some wrong information from this, because to get the information, I'm reading this, I'm using this get current drive parameters, and what I'm thinking is that maybe this is returning me some bad data, or maybe this doesn't work with disks, it only works correctly with floppies. I'm not really sure. I think this might be the problem, but the easiest solution and the best solution right now is to use the extended functions that are in okay, because for disks, disks will grow, disks can be very big, they can definitely be more than 8 gigs in size, so it would be a good idea to use these functions whenever possible, and just use the older ones as a fallback if these aren't supported or something like that. Okay, if there are any questions, I don't see any questions in the chat, so thank you a lot for watching, and I'm sorry I did not get this working, unfortunately. Yeah, as I said, I think I'm getting some bad data from this read drive parameters function. That's what I think might be happening. I am not 100% sure if this is the problem, but this is what I suspect. Okay. Thank you for watching, and we'll see you on Friday. I will do another live stream on Friday. I hope it won't be 4 hours long. I'm hoping at slightly more reasonable live streams, like maybe 1 hour, 2 hours at most. But I don't know. This is kind of how these things go. Sometimes they work, sometimes they don't. So, and yeah, I also had a lot of things programmed. I also had a lot of things that I wanted to do today, and you hit problems, you hit stuff like this when it doesn't work from the first try, and you have to debug and you have to try to figure out, okay, why is it doing that? Why is it not working? And it can take a lot of time to do that. Debugging, yeah, that's all right. Okay, if there are no more questions, then thank you a lot for watching, and see you on Friday. Goodbye. EXT2 support. I don't know. Personally, I don't know. The long story, I probably So my current plan is to, for the main channel videos, not the live streams, for the main videos is to cover memory management. This is the next big topic. And then some of the other basic stuff when dealing with multitasking and user mode, user land. These are the main priority right now. And once I do get past those, I will start going into maybe the VFS. I will go into, I don't know, putting the FAT driver into the kernel, creating a better interface for dealing with everything. Yeah, I hope that answers your question. So it will be a while, but I don't know. I will do X2 at some point. Any other questions? Alright, I don't really see any other questions, so thank you a lot and see you on Friday. And don't forget to like and subscribe and all that stuff you know already. Join the Discord if you're not on Discord, and yeah, see you on Friday. Goodbye. Thank you. Bye bye.